This video goes over Faceplant's different filters and all of their features and controls, as well as using modulation. Filters and synthesizers reshape a generated sound by changing the amplitude of certain frequencies in a sound. Different filter types allow for shaping frequencies in different ways. Filters are what makes a synthesizer a subtractive synthesizer. Subtractive in the way that they can subtract amplitude from the frequencies in a sound in order to create a new sound. I will load an analog oscillator into Faceplant's generator section and add a filter. In the group, while hovering in between the oscillator and the envelope output, a blue dashed line appears. When selected, a drop-down menu appears. Under Effects, I will select Filter. This will add a filter in between the oscillator and the envelope output. This filter is Faceplant's basic filter. It uses the most common filter types: a low-pass filter, a high-pass filter, a band-pass filter, and a notch filter. This filter also has the option for a high shelf, a low shelf, and a peak dip type of filter as well. These graphics represent the different filter types. The graphic farthest left represents a low-pass filter. Low-pass filters allow for lower frequencies to pass through into the sound while attenuating or removing higher frequencies. In other words, low-pass filters subtract higher frequencies from the sound. For demonstration, I will load Ableton's Spectrum device after Faceplant in order to analyze frequencies that happen in a sound. When generating a sawtooth waveform, which generates harmonic frequencies, we can see these frequencies indicated in Spectrum's window. While engaging one of the filter's controls called cutoff, by selecting and dragging, we can hear changes in the sound. The graphic window above the filter selection represents the frequency spectrum and the filter that's being used. This can help you visualize the frequencies the selected filter will be attenuating. When changing the cutoff, we can see it move. This will show where the filter is attenuating in the frequency spectrum. The cutoff frequency sets the point in the filter where it will begin to attenuate frequencies. Attenuate meaning reducing the amplitude of. As I change the cutoff setting, frequencies above where the cutoff is set will be reduced in amplitude and potentially removed altogether depending on where the cutoff is at. Notice in the graphic representing the low-pass filter a line that slopes down to the right. Sometimes synthesizers will just show a graphic when you're selecting the filter type. We can tell that this is a low-pass filter type because graphically the line slopes towards the right, which is towards the high side of the frequency spectrum, indicating that this filter will attenuate higher frequencies. If I set the filter's cutoff's virtual control knob all the way to the right, we can see just below a small window with a number that indicates what frequency the cutoff is set at. With it set all the way to the right, it shows 20.5 kilohertz. This happens to be just above the maximum high side of frequency for sound. We hear sound between 20 hertz on the low frequency side of sound and 20 kilohertz on the high frequency side of sound. With the cutoff all the way to the right, we are allowing all of the frequencies in the sound to pass through into the sound we hear. When I move the cutoff control towards the left as I'm generating the sawtooth wave, we can hear and see in Spectrum that higher frequencies begin to decrease in amplitude. We can also see where in the frequency spectrum frequencies are becoming attenuated or removed, indicated in Spectrum's window. Notice the larger window on the left showing a waveform graphic. With the cutoff set all the way to the right, it shows the sawtooth wave, which is what we have the oscillator set to generate. When moving the cutoff to the left towards the low frequency side of sound, the shape of the waveform changes in relationship to the frequencies that are being attenuated in the sound. This is the waveform shape of the newly generated sound as it passes through the filter. It is possible to remove all the frequencies from the sound if the cutoff is set lower than the sound's lowest frequency content. Notice with the filter cutoff set all the way to the left, it will be set at 20 Hz, the lowest frequency side of sound. With a low-pass filter, if you have the frequency set at its lowest frequency setting, you can potentially remove all the frequencies from a sound. As I move the cutoff back and forth from the high side to the low side, we can hear the effect this has on the sound of the sawtooth wave. While paying attention to the cutoff settings and observing in spectrum, we can see exactly where the frequencies begin to attenuate. In other words, we can see that certain frequencies become decreased in amplitude and, depending on where the cutoff is set at, possibly removed altogether. When using filters for shaping sound, be mindful that if certain frequencies don't already exist in the sound, at certain cutoff settings, this will not have an effect on the sound. Frequencies must exist in a sound in order to be shaped by a filter. Notice there is an angle or slope to how this filter is removing or attenuating the frequencies of the sound. We can see in the graphic representing the low-pass filter that it slopes down to the right. Low-pass filters don't necessarily remove all the frequencies above the cutoff setting. Rather, the frequencies are gradually attenuated. We can see in spectrum at what frequency this attenuation begins. This frequency is where the cutoff is set. For example, if I set the cutoff to around 900 Hz, we can see in spectrum that there are still frequencies in the sound above 900 Hz. They are simply decreased in amplitude in relation to the roll-off or slope of the filter. The slope determines how much and to what extent the frequencies will become attenuated. The slope settings of the filter determine this. On the right side of the filter graphic are the slope settings. These settings are set with multiple values, from 1 times up to 6 times. What these values are multiplying is what is called a pole. In Phase Plant, when you hover over controls or settings, information about it will show in the window bar at the very bottom of Phase Plant's graphic user interface. When I hover over the slope value, FacePlant lets us know that 1 times represents a classic 2-pole filter. Poles are a way that synthesizers use to determine the slope or roll-off of the frequencies being filtered. A 1-pole filter has a slope of 6 decibels per octave. This means that between 1 octave and the next octave above that, the amplitude will decrease by 6 decibels. Looking in Spectrum's window, we see a vertical line that represents octaves, and we see numbers on the left that represent amplitude in decibels vertically. If you make a point from 1 octave to the next and decrease the point at the octave above by 6 decibels, and picture a line between the points, you will be able to visualize the slope of a 1-pole filter. The 1 times represents a 2-pole filter. With this, rather than decreasing 6 decibels per octave, it will decrease by 12 decibels per octave, 2 times 6, a steeper roll-off than the 1-pole. You can set Phase Plant slope up to 6 times, which is a 72 decibel decrease per octave. This is fairly steep. With this setting, much more of the higher frequencies will become attenuated than with a lower setting. Basically, the higher the setting, the steeper the slope, or roll-off of the frequencies being filtered. With a low-pass filter, this will be the roll-off of the higher frequencies. We can see the slope represented in the graphic of the low-pass filter. Notice the angle of the slope changing when you change the slope settings. If you select another filter graphic, the filter type will change. I will select this one, which is a high-pass filter. With a high-pass filter, the frequencies that will attenuate will be the lower frequencies. High-pass filters attenuate frequencies below the cutoff setting. That is, they allow for higher frequencies to pass, while attenuating or removing lower frequencies from the sound. The opposite of a low-pass filter. The slope settings work the same for the high-pass and the low-pass, except on opposite sides of the frequency spectrum. If we generate a sound and change filter types and their settings, we can listen and compare how these filters differ and how they are affecting the sound. As well, we can see in spectrum exactly how the sound is being affected. The control to the right of the cutoff, called Q, allows the filter to boost in amplitude rather than reduce the amplitude of any frequencies that are happening around where the cutoff is set. We can see in the filter's graphic at the cutoff frequency a peak that increases or decreases when the Q's value is adjusted. With the Q increase, as I generate the sawtooth wave and change the cutoff settings, we can hear how this affects the sound. We can also visualize in spectrum exactly what is happening to the frequencies in the sound. This creates what I can describe as a sharper edge in the way it affects the sound as you move the cutoff settings through the frequency spectrum. We can see and listen while adjusting the cutoff as it's moving through the spectrum, and what I also think really gives a filter its distinct character. Faceplant calls this control Q, but it is also commonly referred to as resonance. Some synthesizers call this Q or emphasis, but resonance is more commonly used. I will switch the filter type to this one here, which is called a bandpass filter. A bandpass filter attenuates the frequencies on either side of where the cutoff frequency is set. You might say it is like a low pass and a high pass together. We can listen and visualize the effect that this filter type has on the generated sound while changing the cutoff and Q settings. When you adjust the Q with this bandpass filter, we can see graphically the peak at the cutoff setting increasing and decreasing. With a low Q setting, this filter will not have a distinct effect on the sound. You will most likely want to increase the Q value while using the bandpass filter. Once again, we can get a feel for how this filter type may shape a sound by listening and visualizing in spectrum with different settings while filtering the sound. I will now change to this filter type here, which is called a notch filter. Notch filters are also sometimes called band stop or band reject filters. With this filter type, we are allowing for frequencies in the generated sound to pass on either side of the cutoff, while attenuating frequencies that happen around the cutoff setting, creating a notch of attenuated frequencies. You might say opposite of a bandpass. We can hear the effect this filter type has on the generated sound while adjusting the settings. With high Q values set, the notch of potentially attenuated frequencies almost disappears with the notch filter. With high Q settings, this notch filter will have little effect on the sound. The low pass, high pass, band pass, and notch filters are the most common types of filters you will find in synthesizers. This filter has a few more. The graphics in the filter window to the right of the common filters are shelving types of filters. Shelving allows you to adjust the level or gain of the frequencies from where the cutoff frequency is set. You can either boost or cut the amplitude of the affected frequencies. That is, increase or decrease the amplitude of. Notice the control knob for gain settings to the right of the Q settings. Unless you select one of the shelving types, this knob will be grayed out. The control does not have any effect on the other common filter types. I will select this shelving type here. This one is a low shelf filter. Just like the other filter types, the cutoff frequency sets the point in the filter where frequencies will change in amplitude. With the gain set right in the middle at 0 dB, the shelving filters will not affect the sound. We can see this represented in the filter's graphic as well, with a flat line across the graphic. With the low shelf selected, while increasing the gain, we can see graphically that any frequencies in the generated sound below the cutoff settings will be increased in amplitude. If we decrease the gain, those frequencies below the cutoff will decrease in amplitude. With the gain all the way down, the filter's graphic will look similar to a high-pass filter. But with shelving filter types, we are not completely removing the frequencies. We are simply lowering the amplitude of the affected frequencies. When you adjust the Q, we can see visually the slope change and how this will affect the generated frequency's attenuation. With high Q settings, we are creating peaks and dips on the low and high side of the cutoff settings. The filter's graphic is a great way to visualize this, but the best way to determine how the settings affect the generated sound is to listen with different settings. The graphic all the way to the right represents a high shelf filter type. This behaves exactly like the low shelf, but opposite. With a high shelf, we are increasing or decreasing the amplitude of the generated frequencies that are above the frequency cutoff setting. We can listen to how this filter will affect the sound of the sawtooth wave. The shelving filter in between the high and low shelf filters is a peak dip type, sometimes called a bell. This peak dip shelving type increases or decreases the amplitude of the generated frequencies that are happening at the cutoff settings, similar to the bandpass and notch filters. The Q adjusts the range of these attenuated frequencies. We can hear and visualize the effect this will have on the generated sound while trying different settings. Like most synthesizers for creating sounds that evolve and change over time, rather than manually adjusting the setting, we commonly use modulation for adjusting the settings, thus creating a change in a sound over time. I will demonstrate this by modulating the filter's cutoff frequency settings using an envelope. I will add an envelope to Faceplant's modulator section. Then I will route the envelope output to the cutoff frequency. I will set the envelope's attack to about 3 seconds and set the modulation amount to 25%. And I will set the cutoff to around 400 Hz. Now when I play a note, the filter's cutoff settings will move from 400 Hz to above 2 kHz for around 3 seconds. Faceplant's modulation settings indicate the frequency change that will happen at different settings. We can see here that with the cutoff set at 400 Hz, with a modulation amount of 25%, the cutoff will move to about 2.26 kHz when a note is played. Larger amounts of modulation will move the cutoff frequency with greater changes in frequency. With 60% modulation amount set, the cutoff moves from 400 Hz all the way to the high frequency side of sound, which is 20 kHz. If I set the envelope to have just an attack and decay set to around 3 seconds, when I play a note, the cutoff frequency will move up to the high frequency side for around 3 seconds, then back to 400 Hz for another 3 seconds. If I set the amount of modulation to 100%, And with the same envelope, when I play a note, the cutoff frequency will increase to the maximum high side of the frequency spectrum at 20 kilohertz and hold there for a second. And then will decrease back to where it started from at 400 hertz. The reason the cutoff frequency holds at 20 kilohertz is because at a 100% modulation amount, the cutoff would move from 400 hertz well above 20 kilohertz. So it would take some time for it to reach that high point above 20 kilohertz and then move back down below 20 kilohertz. We don't hear anything that is happening when the cutoff would cross above 20 kilohertz because humans cannot hear frequencies above 20 kilohertz. And the filter's controls do not go above 20 kilohertz as well. With the same envelope, if I set the envelope's modulation amount to a negative setting, the cutoff frequency will start by moving towards the low frequency side of the spectrum, then increase back to where it started from, behaving the same way as the positive setting, but changing in the opposite or negative way. Positive settings moving the cutoff towards the high side, and negative settings start off by moving the cutoff frequency towards the low side. These combined settings are the types of things you must consider when using a filter to create a change in a sound. The first consideration is what frequencies are in the sound to begin with. The next consideration is where in the frequency spectrum of the sound the cutoff will begin attenuation. This is the frequency you have the cutoff set at. The next consideration is what kind of changes in the sound you want to have happen over time. All of this depends on the envelopes as well as the filter settings. If you are using another modulator, for example, an LFO for modulating a filter rather than an envelope, all of these considerations will apply in the same way. You must consider how the settings values of the modulator you are using will happen over time, how the values of the modulator will change over time. You must also consider the type of filter you are using and the effect it will have on the sound, and how the modulator settings affect this change in the sound. The subtleties and nuances of shaping a sound with filters takes practice. Using a spectrum analyzer can help, but I think the best practice at first is to critically listen while you make small adjustments. I think making smaller adjustments while you critically listen and compare is a good practice for finding and creating the small details you are looking for in a sound design. Phaseplant's default filter is a great starting point, but Phaseplant does offer other filter types. I will remove the default filter from this sound by selecting the X in the upper left corner. Then I will add Phaseplant's nonlinear filter in between the oscillator and the output. A feature of the nonlinear filter that the default filter doesn't have is the option for drive. Filter drive is a control on a synthesizer that adds gain to the signal before it enters the filter, intentionally creating saturation and distortion. This process overloads the filter, which changes the timbre of the sound by adding harmonics and making it a richer or harsher sound. It is an effective way to add warmth, grit, or aggressive distortion to a sound. Phaseplant's nonlinear filter models this behavior. Like Phaseplant's basic filter, this nonlinear filter has the option for a low pass, a high pass, a band pass, and a notch filter type. This filter also has what is called an all-pass filter. All-pass filters simply pass all the frequencies into the sound. What makes this filter useful and how this filter adds character is with the drive settings. Drive affects the frequencies that are happening around the cutoff frequency. With the all-pass filter selected, I will increase the drive settings and change the cutoff frequency. We can visualize and hear how this affects the sound while changing the settings. We can visualize how drive is affecting the frequencies while paying attention to spectrum. The graphic for the filter type reflects this as well. Notice the peaks and dips that are happening around the cutoff frequency, especially with higher Q settings. We can see that at different drive amounts, there are small peaks and dips in the graphic. This reflects how the frequencies will be boosted or attenuated. You can visualize this in the other filter types as well. The best way to know how drive will behave in different filters and how it will affect the sound is to try and compare them. The drive characteristics give filters a unique quality and character. In different synthesizers, we get different characteristics. Even though most synthesizers use the most common filter types, each synthesizer has a subtle quality that differs from one synth to the next. This is one reason why we may want to have the option for many different filters. For example, a Prophet 5's filter versus a Mini Moog's filter will have their own unique character. With the nonlinear filter, we can choose from different drive modes. If you select in the drop-down menu next to Mode, you can see the different drive mode options for this filter. Each mode has its own unique character. Once again, the best way to know what each of these modes will do and how they will affect the sound is to try them, while also visualizing in a spectrum analyzer and critically listening while you're making adjustments. Analog drive characteristics in software synthesizers often are modeled after analog synthesizers. For example, Faceplant has the option to use a filter that models a ladder filter. I will delete the nonlinear filter and select in Faceplant's effect lane. When I do this, we can see a drop-down menu with the options for different types of effects. One of them is a ladder filter. I will select this device. When I insert a device in the effect lane, the audio signal path will start in the oscillator, which is routed to the envelope output, which passes the audio from the output to the effect lanes, which then passes through the inserted devices. The traditional analog signal flow starts with the oscillator, then the filter, then to the amp. But it is not uncommon to use filters as effects after the amp output. Analog synthesizers use electricity for generating their sound. A ladder filter is called that because the electrical circuit diagram of the original design, patented by Bob Moog, resembles a ladder. This type of filter has its own unique characteristics and why Moog synthesizers are still desired for their analog sound quality. Faceplant's ladder filter models the way this analog circuit behaves on the electricity and sound in order to achieve a comparable ladder filter-like sound. Just like the nonlinear filter, this filter has a drive setting which gives it its unique qualities. The ladder filter is a low-pass filter type. For the drive settings to work, you must select and turn on the saturation right here. We can see the cutoff frequency control here and a resonance control. Resonance is equivalent to the Q control in the nonlinear filter. It boosts the amplitude of the frequencies around the cutoff frequency. As well, it affects how the cutoff will shape the frequencies. The diode selector selects between a modeled transistor ladder and a modeled diode ladder topology in the circuitry, which affects the cutoff's shaping in different ways. The bias selector simulates bias voltage over the electrical components, which also affects the sound in different ways. As with everything in synthesizers, the best way to hear how it will affect the sound is to try it while critically listening. Another filter option in Faceplant is a comb filter. A comb filter creates a frequency response with a series of regularly spaced peaks and notches in the frequency spectrum that resembles a comb. Time-based effects can create this type of effect as well. With time-based effects, this causes certain frequencies to reinforce each other while certain others cancel out due to phase relationships between the different frequencies, which creates the peaks and dips that resemble a comb. A comb filter creates the peaks and dips with its filter qualities, similar to the way drive settings create peaks and dips. There are always many ways to certain or similar sounds with different methods in different synthesizers. The cutoff frequency with the comb filter is displayed as a numerical value rather than as a knob, but still sets the point in the filter where the sound is affected. With this filter, it sets the distance between each peak. The polarity settings sets troughs with peaks and vice versa, with the plus settings having a peak at 0 Hz. In the minus settings, having a trough at 0 Hz. The stereo setting flips the polarity setting for the right channel, allowing the comb filter to be used for mono-compatible stereo widening. In mono, one speaker is used. In stereo, 2 speakers are used. In audio, polarity refers to the positive or negative voltage of a signal relative to a central median line, essentially determining whether a speaker cone pushes or pulls. This is one example of how phase relationships between frequencies may affect sound. The mix knob controls the level between the unaffected dry sound versus the affected filtered sound. Another type of filter that Faceplant offers is a formant filter. A formant is a specific band of frequencies that become resonant and create vowel-like sounds. Formants are boosts in amplitude of specific frequency ranges. The human vocal tract creates these resonant frequency peaks. In this way, when speaking, the vocal cord is like an oscillator, and the vocal tract is like a filter. The blue circle in the formant filter's graphic window selects between 2 frequency ranges to boost. It works on an XY grid, where vertical and horizontal movements determine the boosted formants. You can select and hold and drag the blue circle around the window to create formant changes. In the background of the window, there are small letters that represent vowel-like sounds. As I drag the circle around the XY grid in the window, we can hear the effect that this has on the sound. When you apply modulation to this filter, there is a routing option for the x-axis which determines the horizontal movement, and a routing option for the y-axis which determines the vertical movements. The Q settings adjust how powerful and narrow the frequency boost is. The low selector allows low frequencies through the filter, and the high selector allows high frequencies through the filter.